Hi everyone, I'm Mahesh, a postdoctoral researcher at CISPA. In this video, I will be presenting a recent work titled Incompressible Functional Encryption, which has been accepted at ITCS 2025. This is a collaborative work with Rishabh Goel from the University of Wisconsin-Madison, Venkatakopala Aman Verma from IIT Delhi, and myself carried out during my postdoctoral tenure at IIT Delhi. Let's begin with a quick introduction to functional encryption schemes. A functional encryption scheme is an advanced encryption scheme that introduces a more refined approach to data access. Like conventional encryption, FE involves two keys, a master public key that can be used to encrypt messages, a master secret key capable of decrypting any ciphertext encrypted under the master public key. However, the distinguishing feature of functional encryption lies in its selective decryption capability. Consider the following scenario. Alice encrypts a message M using the master public key. In traditional encryption, if Charlie has access to the ciphertext and the secret key, he can fully decrypt to retrieve the message. In contrast with functional encryption, Charlie does not learn the entire message. Instead, he should only learn the result of a specific function F applied to the message. Bob, as the holder of the master secret key, can derive function-specific decryption keys. This means Bob can generate a decryption key for F, which allows Charlie to decrypt the ciphertext and obtain F of M, but nothing beyond that. Importantly, this process does not require Bob's continuous involvement. Once the key for F is issued, Charlie can decrypt future ciphertext independently, even if Bob is unavailable. In essence, functional encryption introduces fine-grained access control over encrypted data. A functional encryption scheme consists of four algorithms with the following syntax. The setup algorithm generates the master public key and master secret key. The encryption algorithm takes as input a master public key, a message, and outputs a ciphertext. The key generation algorithm takes as input a master secret key, a function from an appropriate function class, and outputs a secret key. The decryption algorithm takes as input a secret key associated with a function F, a ciphertext, and outputs F of M, where the ciphertext encrypts the message M. Formally, the security of a functional encryption scheme is defined through a game-based framework. The security game proceeds as follows. A challenger initializes the functional encryption scheme by running the key generation algorithm. The master public key MPK is then sent to the adversary, while the master secret key MSK is kept hidden. In the next phase, the adversary is allowed to query for secret keys for functions F. It is allowed to make multiple number of queries of its choice. In the challenge phase, the adversary selects two plaintext messages, M0 and M1 of its choice, and sends them to the challenger. The challenger randomly selects a bit P. It encrypts the chosen message MB using the master public key MPK to produce a challenge ciphertext C. The challenge ciphertext C is then sent back to the adversary. An important point that M0 and M1 must satisfy is that for any function F queried in the previous phase, the value of F of M0 must be equal to the value of F of M1. Again, the adversary is allowed to query for more secret keys with the constraint that F of M0 is equal to F of M1. Then the adversary attempts to guess the value of the bit B. The adversary wins the game if its guess B dash matches the actual bit B. We say that the functional encryption scheme has standard security if for any efficient adversary, the probability of correctly guessing is close to half. In other words, the adversary's advantage is negligible, making it no better than a random guess. But this security definition has a few limitations. For example, the master secret key must remain completely hidden from the adversary, as its exposure allows the generation of a secret key for any function. In fact, the adversary wins if it obtains even a single key for a function F such that F of M0 is not equal to F of M1, enabling the adversary to distinguish the ciphertext. Such a secret key will be called a distinguishing key. It is unrealistic to expect that all secret keys should be securely stored, as the number of users in the system can be thousands or even millions. The scenario of an adversary obtaining the entire secret key has been studied in the context of regular secret and public key encryption scheme. It It is important to note that the security cannot be guaranteed if the entire secret key and the entire ciphertext are accessible to an adversary. This limitation arises directly from the correctness of the encryption scheme. This is where the idea of incompressible encryption comes into the picture. Proposed by Dziembowski and further extended by Guan et al., incompressible encryption addresses scenarios where the adversary may gain access to the entire secret key but parts of the ciphertext. The central idea is to make the ciphertext so large that it becomes practically impossible for the adversary to store the entire ciphertext over a long period of time. In a security game, the adversary gets a challenge ciphertext CT star, which is either an encryption of M0 or M1, and then has to compress its storage. This reduction in storage will make the adversary unable to store the entire ciphertext. Later, when the adversary receives the entire secret key, it still should not be able to distinguish the ciphertext. This reduction of storage is justifiable because long-term storage is either difficult or too expensive. Let us review prior works in the area of incompressible cryptography. As mentioned in the previous slide, the concept of incompressibility was first introduced by Dziembowski, who proposed an incompressible SKE scheme. His constructions were designed to be secure even against unbounded adversaries, that is, adversaries with no computational limitations but bounded storage capacity. Building on this idea, Guan et al. Extended the notion of incompressibility to the public key setting. They developed two distinct incompressible PKE schemes. The first construction was generic and could be instantiated using any standard PKE scheme. However, it suffered from a poor rate where the rate is defined as the ratio of the message size to the ciphertext size. The second construction achieved optimal rate. However, this scheme relied on indistinguishability obfuscation, a powerful and computationally expensive cryptographic primitive. Later, Branco et al. Presented rate 1 incompressible encryption scheme for both the secret key and the public key setting. Their constructions achieved incompressibility from standard cryptographic assumptions, avoiding the reliance on I/O. Additionally, their PKE scheme was designed to be secure against chosen ciphertext attack. Subsequent work by Guan et al. Explored the concept of incompressibility in the multi-user setting. The primary goal of our work is to generalize the concept of incompressibility to functional encryption scheme. We begin by introducing three distinct levels of security, which depends on whether the adversary is provided with a master secret key, or unboundedly many distinguishing keys, or just a single distinguishing key. Next, we present multiple incompressible FE schemes, each with its own efficiency parameters that are not comparable to each other. Finally, we introduce incompressible attribute-based encryption schemes based on standard assumptions, where ABE schemes are considered a weaker variant of FE schemes. Let us now look at the incompressibility security definition for functional encryption. This game is divided into two major phases, each phase having its own adversary. The first phase of the security game is very similar to the standard security, where the challenger generates a pair of master keys, the adversary is allowed to query on secret keys, then it sends two messages of its choice and obtains a challenge ciphertext. After it queries for more functional keys, it does not guess the bit B like in the standard security. Whereas it compresses the challenge ciphertext to a state such that its size is bounded by a parameter S. In the second phase, the second adversary is provided with the master public key and the state generated by the first adversary. It can then query only a single distinguishing key and receive the secret key SKF. The adversary attempts to guess the value of B. It outputs a bit B dash as its guess. Again, the adversary wins the game if its guess B dash matches the actual bit. We call this notion as regular incompressible security. It is easy to see that if a scheme satisfies incompressible security notion, then it also satisfies the standard security notion. We can define more variants of incompressible security notions as follows. The second adversary can adaptively query on unboundedly many distinguishing keys of its choice and obtain them instead of a single distinguishing key. We call this notion as semi-strong incompressible security. We can also define a stronger notion where the adversary obtains the master secret key, and this is called strong incompressible security. I will now present the main results of our work. We construct multiple incompressible FE schemes that rely on minimal assumption of regular FE schemes. We first construct a semi-strong incompressible encryption scheme with short keys. When the FE scheme is instantiated with the rate 1 selective secure FE scheme of Jain et al., we achieve the first result. If instead we use the rate half adaptive secure FE scheme of Jain et al., we obtain the second result, which is adaptively secure. A scheme is selectively secure if the adversary must submit its choice of messages at the start of the security game before seeing the master public key. We also provide a rate 1 semi-strong incompressible FE scheme where the ciphertext rate is optimal, but the scheme involves large secret keys. Additionally, we construct a rate 1 regular incompressible FE scheme that achieves optimal rate but uses short keys, with the condition that the functions output only a single bit. Finally, we present a rate half incompressible attribute-based encryption scheme with short keys. This scheme achieves adaptive security under the sub-exponential learning with error assumption. We would like to emphasize that in a follow-up work, we show that except for the second construction, the remaining constructions are optimal in terms of ciphertext rate and secret key sizes. I will now present the core ideas used in our FE construction. The idea is that to ensure incompressibility of the FE ciphertext, we will use an incompressible PK scheme inside of a regular FE scheme. The plan is to use the incompressible PK scheme to encrypt the actual challenge message and put that inside the base FE scheme such that only distinguishing keys decrypt the incompressible PK ciphertext, while the non-distinguishing keys keep on using the message that is directly encrypted within the FE ciphertext. In a bit more detail, during setup, we sample an incompressible PKE public secret key pair along with an FE master public secret key pair. To encrypt a message M, we run the base FE encryption algorithm to encrypt a message M with a flag bit B and an incompressible PKE ciphertext. Typically, the encryptor sets the flag bit B equal to 0 and encrypts an all-0 message inside the incompressible PKE ciphertext. Now, to create a secret key for some function f, the key generation algorithm defines an expanded function f hat with the following description. It takes as input a message, a bit B, and an incompressible ciphertext. If the bit B is equal to 0, it outputs f of m. The bit B set to 0 denotes that this is a real-world scenario. Again, the function outputs f of m if f is a non-distinguishing function. Recall that a non-distinguishing function is a function such that f of m0 is equal to f of m1. Now, if the function f is distinguishing, it will first decrypt the incompressible ciphertext, apply the function on this message, and output that value. Clearly, the above scheme is correct. To prove security, our plan is to switch a real-world encryption of the challenge message MB, which is an FE encryption of MB0 incompressible ciphertext of all 0 messages, to an FE encryption of M01 incompressible ciphertext of MB. This should follow from regular FE security as for any distinguishing and non-distinguishing secret key, both ciphertexts would have the same result. Once this happens, we hope to reduce the security to incompressibility security of the PKE scheme. The above template has two issues. First, how to secretly encode whether the function f is distinguishing or not inside the function f hat. Second, how to ensure that a non-distinguishing key does not contain any information about the secret key of the incompressible scheme. I will now show how to resolve these issues and obtain a variant of our first construction. This variant achieves a rate half but has large secret keys. The construction requires 3 key components: a regular FE scheme, a regular SKE scheme, and an incompressible PKE scheme. The master public key is a pair of FE master public key and an incompressible PKE's public key, whereas the master secret key is the pair of the corresponding secret keys. To encrypt a message M under the master public key, the algorithm first generates an incompressible ciphertext that encrypts an all 0 messages using the incompressible PKE. Next, the function encryption scheme is used to encrypt the set consisting of the message M, the bit 0, incompressible ciphertext, and a bot symbol. The key generation algorithm takes as input the master secret key and a function f. It generates the functional secret key for the function f hat, which has the following description. It has an SKE ciphertext that encrypts an all-zero message. It takes as input a message M, a bit B, an incompressible ciphertext, and an SKE secret key. If B is equal to 0, it simply returns f of M. In the real-world scenario, a valid ciphertext would have the bit set to 0, hence the scheme provides the necessary correctness. Whereas in the security proof, the bit B in the challenge ciphertext is set to 1. Again, it would output f of M if B hat is equal to 0. This bit is obtained along with a secret key of the incompressible PKE scheme by decrypting the SKE ciphertext using the SKE secret key. If B hat is not equal to 0, it decrypts the incompressible ciphertext, applies F to the decrypted message, and outputs the result. Essentially, the bit B hat indicates whether the function is distinguishing or not, which is crucial in our proofs, hence resolving our first issue. Observe that the secret key of the incompressible PKE scheme is now available to function F hat in an encrypted form as an SKE ciphertext, and this resolves our second issue. Now, let's analyze the parameters of the scheme. We start by assuming that the underlying FE and incompressible PKE scheme have rate 1. Therefore, the rate of the scheme is half because the size of the ciphertext is size of the message plus 1 plus size of the message plus a polynomial in the security parameter. The size of the functional keys is large because the description of the extended function f hat contains f and an SKE ciphertext, and this ciphertext is an encryption of the secret key of the incompressible PKE scheme. In a follow-up work, we have shown that rate 1 incompressible PKE schemes have secret key as long as the length of the message. Now let's discuss the security of our scheme. We will prove it using a sequence of hybrid arguments. To keep things simple, we will focus on regular incompressible FE security, where the first adversary does not request any secret keys. The second adversary makes a single distinguishing key query. In hybrid 1, the game runs as per the original security definition. In hybrid 2, we modify the incompressible ciphertext within the challenge ciphertext to encrypt the message MB. This modification is secured due to the standard PKE security property, as the PKE's secret key is not required anywhere in the game. In hybrid 3, we modify the distinguishing keys generation. Instead of encrypting an all-zero message, the SKE ciphertext now encrypts the bit 1 and the incompressible PKE secret key. This change leverages the security of SKE scheme. In hybrid 4, the challenge ciphertext is changed once again. It now encrypts a set containing M0, the bit 1, the incompressible ciphertext of MB, and the SKE's secret key. The distinguishability of this step follows from the security of the FE scheme. In the final hybrid, we change the incompressible ciphertext within the challenge ciphertext into an encryption of 0. This follows from the incompressible PKE security because the secret key is used in the generation of the distinguishing key. Now, I will present our rate 1 incompressible FE construction with large secret keys. The construction requires 3 key components: a regular FE scheme, a regular SKE scheme, and an extractor instead of an incompressible PKE scheme. Let us briefly recall the concept of an extractor. An extractor is a deterministic function that takes as input a string R and a seed S and produces an output string. It satisfies the following security. The distribution consisting of the triplet containing the seed S, the extractor's output on inputs R and S, and a leakage on R is statistically close to the distribution of the triplet containing S, a uniformly random string, and the same leakage on R. In other words, the output of an extractor looks random, even if an adversary obtains the seed and a leakage on R. For the sake of simplicity, we will assume that the function's output size is equal to the size of the seed of the extractor. The master public key is an FE master public key, and the master secret key is the corresponding master secret key. To encrypt a message M under the master public key, it performs an FE encryption on the set consisting of the message M, the bit 0, and the bot symbol. To generate a secret key for the function F, it first generates a function F hat with the following description. It has an SKE ciphertext that encrypts an all-zero message. It takes as input a message M, a bit B, and an SKE secret key. If b is equal to 0, it simply returns f of n. Whereas if b is equal to 1, it first decrypts the SKE ciphertext using the SKE secret key to obtain the bit b hat, a seed s, and a string b. If the bit b hat is equal to 0, it outputs s. Otherwise, it outputs f applied on v, XORed with the output of the extractor on input m and s. Now, let us analyze the parameter of the scheme. We assume that the underlying FE scheme has rate 1. Therefore, the rate of the incompressible FE scheme is 1 because the size of the ciphertext is size of the message less a polynomial in the security parameter. The size of the secret keys are large because the description of the extended function f hat contains f and an SKE ciphertext, and the ciphertext encrypts the string v, which is as long as the message m. To prove the security of the scheme, one can change the SKE ciphertext to encrypt the set containing bit 1, a seed s, and the challenged message XORed the output of the extractor on input r and s. The indistinguishability follows from the SKE scheme security. Next, the FE ciphertext can be changed to an encryption of r, the bit 1, and the SKE secret key using the FE security. Finally, using the extractor property, we can change the SKE ciphertext to an encryption of bit 1, a seed s, and a truly random string, thereby removing all information of b from the entire game. Recall that the secret keys of the rate half constructions are large. Interestingly, to reduce their size, we incorporate a rate half incompressible PKE scheme along with an additional layer of SKE encryption. By plugging the rate half adaptively secure FE scheme of Jane et al. In the above scheme, we obtain a rate 1/4 adaptively secure semi-strong incompressible FE with short keys. The rate 1 incompressible FE can be modified to a scheme with short keys by restricting to Boolean functions. We will now focus on our constructions for incompressible ABE schemes. First, assuming the sub-exponential hardness of LWE problem, we present an incompressible ABE scheme for predicate classes represented by circuits of depth D with the following parameters. The construction uses a two-leveled deferred encryption technique, and we believe that this technique could find more applications in other contexts. For more details, please refer to the full paper. Second, we give a construction from minimal assumptions of regular ABE by extending ideas of Guan et al. I will now conclude my talk by highlighting a few future directions. Recall that our rate 1 schemes are only selectively secure. So firstly, can we build rate 1 semi-strong incompressible FE with adaptive security? It would be really interesting to see a construction for strong incompressible FE with either selective or adaptive security. Designing strong incompressible ABE or IBE from standard assumptions is another interesting problem. And finally, the use of incompressible cryptography to build other primitives is still unexplored. Thank you.